I will start. So, a very good afternoon, Suhaila ma'am and dear participants. We are at the third session of day 4 of this AICT Training and Learning Atal Academy sponsored faculty 1-week online faculty development program on photonics, organized by Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur. At the outset, I would like to welcome Suhaila ma'am from Tunisia for this session on active learning in developing countries, some examples in teaching optics. At the beginning, I would like to ask my colleague, Mr. Swapnil, to introduce Suhaila ma'am. Mr. Swapnil, please.
Thank you, sir. After hearing a beautiful lecture on cognizance of health, I can say distance doesn't matter when roots of your relationships are strong enough. And here we have a lady of a fountainhead of illuminating ideas, idol of knowledge, Professor Suhaila Lahmar, madam, all the way from Tunisia. Good afternoon to all. On the behalf of Rajarshi Shahu Mahavidyalaya, Latur, at the outside, I welcome Professor Suhaila Lahmar, madam, and all my dear participants. It is my great privilege to introduce one of the international resource person, Suhaila Lahmar, madam. Currently, she is working as a professor at Institut Préparatoire Etudes, Scientifiques at Techniques, Tunisia. She completed her PhD in quantum chemistry at the University of Paris, France. Soon after, she was assistant professor at the Faculty of Science of Tunis and researcher at a laboratory of atomic and molecular spectroscopy and applications. Also, she completed her doctorate in the field of theoretical chemistry, molecular spectroscopy, and pollution. After that, she was associate professor at the Faculty of Science, Bizet. She knows Arabic, French, English, Italian languages, out of which Arabic is her mother language. Madam has started her career in the year 1978 as a teacher at a secondary school. Her interested teaching fields are electromagnetism, quantum mechanics, atomic physics, optics, and lasers. She was co-responsible for physics teaching at IPST, Institut Préparatoire Etudes Scientifiques at Techniques, Tunisia. Also co-responsible of exams at national level for recruitment. She is a coordinator and guide of different research projects for PhD and postdoctoral students. She is a referee at various scientific journals, invited speaker at local and international scientific events like workshops, conferences, programs. She is a founder member of Tunisia Society of Optics. She is a renowned resource person at UNESCO International Program in Physics and UNESCO project, active learning in optics and photonics, training of physics trainers, and coordinate of a law project in Africa. One thing I could say, teaching is the act of sharing knowledge we have been given others with the hope that somebody in some way it again will be passed on. Thank you.
Thank you very much for this nice presentation.
Welcome, ma'am. You can now share your screen.
Thank you. Thanks for the presentation. Many thanks, Dr. Yada, for inviting me to participate. Thanks to all the organizers and thanks to the participants. Okay, I'm going to share my presentation now.
Am I audible?
Is that okay?
Yes, ma'am.
Okay. Full screen now?
Yes, yes.
Okay, so I'm sure that in the first session of this activity of your workshop, David Sokolov talked a lot about active learning. But today I will focus on what we can do in developing countries, because when you do active learning in US, it's not the same than when you do active learning in our developing countries. I will give some examples. I will focus on the material, because you can fabricate very simple material without very easily. And we can do active learning for any topic, but we choose optics because the material is very simple. Okay, my colleague introduced me a few minutes before. Just to show you, I am from Tunisia, just show you where is Tunisia. It's this very small country in North Africa, very few inhabitants, 12 millions. It's a Muslim country, mainly Muslim country. As my colleague said before, my first language, my mother tongue is Arabic. French is second, so please excuse my English. It's not very good, but I will do my best. Okay. So as I told you, David spoke about active learning. He told you that the main problem with physics teaching is passive way of teaching, and he gave some solution to overcome this problem. But in our developing countries, we have other problems I will talk about later. And as I told you, I chose optics because it's the material is simple to fabricate. That's it. But you can do active learning for any topic in physics, of course. Okay, I show you here the one of the slides of David's presentation, just to compare passive learning to active learning. In passive learning, the students are there sitting in the classroom, and the teacher is the authority. In active learning, I will show you the teacher the role of the teacher or the instructor will be just as a guide. When students come in passive learning, when they come to classroom, they have some beliefs about physics. If you teach in a passive way, when the students will leave, they will keep their belief will not change a lot. There will be a very small change in their beliefs. When you are in the classroom as the authority, generally you don't allow students to talk together, to discuss together. But in active learning, it's totally different. To encourage discussion between learners. Especially generally when in passive learning, the teachers do not do lab experiments. Especially in our developing countries, lab is very few, because no material, because big number of students and so on. So as you saw on the first session on Monday, and as I will show you in active learning, all the activities are focused on experiment. And in passive learning, when you do lecture...
Excuse me, ma'am.
Sorry.
Bottom right, there is a one patch. Can you minimize? It is covering the content.
Okay. Sorry.
Yes, you can click on minus. Yes. Okay. Thank you, ma'am. Thank you. Please.
So very often the practical activity, the lab activities, are not done in parallel with courses. So students do not make any connection between active practical activities, lab, and with courses. So, as I told you, in our developing countries, the main problem, in addition to passive learning, methods is lack of lab experiment because of lack of material. You can fabricate not everything by yourself, but you can fabricate very cheap material and you can do with in optics and in other physics fields. You can fabricate material very simple, very cheap, and you can do very nice experiments, as I will show you later. You see here, you don't even need a special room for doing those activities. You just use a normal teaching room, but you just need dark. So to have dark, just put some aluminum foil on the windows or black tissue. That's it. Of course, you cannot do active learning every day because it's very time consuming and you have to finish your teaching by the end of the year. So what you can do is do some active learning activities and some interactive lecture demonstration, which works very well with the big number of students in classroom. I will show you some ILDs later. If possible, also, as David showed you, David Sokolov, he showed you some magic tricks that they are very funny and the students enjoy a lot. Okay, what I'm going to present today is inspired from the active learning workshop activities, the UNESCO workshop activities, which includes, it's a week workshop in general, which includes 6 modules, one dedicated to geometrical optics, other one is to lenses, it's also geometrical optics, interference and diffraction, atmospheric optics. For these 2 modules you use the wave model, and as application of what we learn in the 4 first modules are used to show some aspects of optical data transmission and wavelength division multiplexing. You can find the book, the UNESCO book is available on this link, and it's available. Anyone can get it and use it. Okay, I will show you some experiments about geometrical optics, but just want to remind you the 4 steps of active learning process, which are prediction, observation, discussion, and synthesis. PODS, PODS. I will start by this very funny prediction. In this prediction, you have here a cylindrical transparent medium. And you have here a point source. And the question is, sketch your prediction for the rays from the point source incident on the surface at the 3 points. So this is the point source, one ray light incident on this point, another in this point, and another in this point. Okay. Sorry. So before the students do the prediction, you have to show them the material. In this activity, the material is very simple. This is 3 kinds of semi-cylindrical transparent media. This one is in plexiglass. How do you call it? Lucite or plexiglass? This one is a semi-cylindrical container. It's a little bit expensive. In Tunisia, we can't get it because it's not available. So we use either the plexiglass. We use either the plexiglass or, can you see the arrow, Dr. Yada? It's here. Okay, you can also do this by yourself. That container, for this one, we used a cylindrical container for cotton. We cut it in 2 pieces and we closed each piece by this wall in plexiglass, and it works very well for this activity. For the point source, I just want to remember you that the point source is a diverging light source. You can use the torches available in Tunisia, they are available on Chinese market, or you can use the torch of your phone, or you can make a very simple circuit by yourself with the LED battery. This is the circuit. The most expensive here is the battery. Other parts are very cheap. Then you have your diverging point source. Okay, now I will give you few minutes to make your prediction, and then I will, let's say 3 minutes. Think about what will be the answers of students or trainers or inspectors or whatever. Dr. Yadav, do you hear me?
Yes, ma'am. Yes, ma'am.
Okay, so 3 minutes prediction, and I'm still there, but I will.
Yes, yes, yes.
Okay.
Yes.
Okay, I'm going to show you now some.
Yes, ma'am. Yes. Yes, please.
Okay, I will show you some students' predictions. You can see here the students on the board drawing their predictions. This is another. This girl is not sure, so she's asking her colleagues, and they induced her in make prediction in the wrong way. This is here you can see other predictions. Okay, many predictions from students.
Yes.
You see they are different. We will come back to those. These are predictions of teachers. So
yes,
you can see almost the same mistakes than students. Here are inspectors. Also, same problem. Okay. After getting the prediction, you have to ask the participants or the students to agree about, if possible, about one prediction. Generally, in this activity, we never get agreement. So the best way to see what happens is to do experiment. And this is what you see with experiment.
Yes.
With this diverging light source, you cannot see the rays. But
Yes.
the result is there. This transparent chamber is acting as a lens. If you want to see the way of one particular ray, you can use laser to simulate qualitatively what happens to a particular ray. Because the laser is not diverging like as you know, of course, like a point source. It's almost parallel rays, so you can see what happens. So if I come back to, you can see here with any ray, you have reflection there, you have transmission there, and another transmission here, but you have also reflection there. You cannot see it because the percentage of reflected light is very weak. But you have reflection here, maybe once again here, another. So this is what happens in this case. So those are qualitative observation about reflection, refraction, and so on. You can do, using once again the ray model, you can do some more quantitative activities. So about if you see what happens in this separation, here you have air, here you have the transparent medium with his characterized by his refraction index. You can the photo is inverted, but the incident ray is there, the reflected ray is there. This angle, this is the incidence angle, this is the reflection, and this is the transmitted light with the refraction angle. You can give, so the participants can draw a lot of ray with different incidence. They can draw the reflected ray, do measurement of angles, and this is this is a figure done by one good, yeah, with the incidence, with the refraction here. So you have reflection here, and you can easily sorry, you hear me?
Yes, ma'am. Yes, ma'am. No problem.
Okay. So you can check the Snell-Descartes laws. You can also see what happens when light comes from the media with the higher index to the lower index media. This is what happens here in this separation. So the light will come from here, undergo reflection and refraction. You can see it clearly on this diagram. And you can see that as you increase the angle of incidence, there is a limit angle, a critical angle. If the incidence angle is greater than this critical angle, you will have no more a transmitted ray, and you will have what we call total internal reflection, which is a very useful phenomena in optics. As you know, it's used in optical fiber. As you can see on this diagram, if the curvature here is allows, and the index allows total internal reflection, you see that the ray will stay trapped in the optical fiber. You can do this. I don't know if David showed this in the first session, but you can see easily how to do this. Just use a plastic bottle of white with a hole. The light is coming from there. This is a red laser. And you can see that inside of going straight, because I showed you before with laser, the ray is curved, and this stream of water is acting as an optical fiber. This is the same experience when we turn the light off. And as I told you, this is the principle of working of optical fiber. Here I have the laser beam. This is an optical fiber, and just to show that the optical fiber will take the light from there to there, and even if the fiber is not straight, you can change the way of the light. Okay, another experiment, very simple. The one David showed you in the beginning day. What happens with lenses formation, image formation with lenses? So this is a lens. It could be our semi-cylindrical chamber. This is optical object. Of course, it has to be light there. And if you ask to students or mainly teachers to draw the image of this object, light object by this lens, you will get immediately the answer. Where they use 3 particular ray diagrams and they draw the image. They are able to tell you that it is inverted, and so on. But if you ask what happens if you cover the half of the lens with a card, dark, non-transparent card, generally the answer will be very quickly half of image, or as David showed you in his presentation here. He's covering half of the lens, and you see that the image is always there. The only difference is that this point is dimmer because less light. That's it. Part of the light which was coming from here is blocked by the. So to have this image, you don't need, even if you block this part of the lens, you don't need this ray. You can get the image of B by all the other rays coming from this side and going to the. If you, if you show students what happens, really happens, they will never forget that. But if you tell them, if I do this, you will have this, I'm not sure they will get the idea. But if I cover half of the object, that is the arrow, of course you will get half of image because you will not get light coming from the object. You can do more qualitative experiments with lenses. You don't need very expensive material. You just generally, you see the lenses here. Oh, sorry. The lenses here, generally, I get them from opticians, those who make glasses for eyeglasses. Generally, they have some remaining lenses they do not use, so they give me for free. So you can get, here you have positive lenses. You can get many kinds of lenses, negative and so on. And you can see very clearly here you have a torch with arrow, light with arrow. You put your, you hold your lens here with a piece of clay, or can find any solution to hold your lens, and you get here the image as showed on this diagram, inverted, could be smaller, or it could, the size of the image comparatively to the object depends on the distance between the object and the lens, and also the distance, no, only this distance. So it could be the size of the image depends on this distance object. You can see what happens when the torch is very far from the lens. That is, your rays come from parallel rays coming from the infinity, and you can do quantitative measurements just by putting a kind of ruler or meter here. You can measure the distance between the lens and the object, and see the size of the image, and see that when the object is at infinity, the image will be on the focal point of the lens. Till now, I mean, you can do a lot of more experiments, quantitative experiments with lenses. Do what happens if you put diverge, if you have an image here, if you put another with this lens, you put a diverging lens, you can see that the position of the image will be will move, it will be it will be further, and so on. So you can do many experiments. All those experiments are based on the ray model. I mean, in this experiment, if I ask you to, because the ray model, as any model, it has limits, especially in what I will show you here what will happen to the ray model. In this experiment, we have a slit. Here we have parallel rays coming from laser, and the question is, what will happen on this screen? For the slit, you can make very easily single, especially for single slit as you have here. You can do single slit very easily by cutting slits on mirrors, or using black tape on some transparent piece of glass or anything. It's very easy to make single slits. So what will happen here if we assume that geometrical optics is still working, geometrical optics, I mean the ray model of geometrical optics is still working, you are expecting that the rays will continue here. They will be blocked by this part of the obstacle, and here they will continue their way, since this is the slit. But what the experiment shows is you don't have only light is not only there, but you have light in the middle and other, let's say, fringes. This is diffraction. This is what we call diffraction. And when the obstacles here, because in geometrical optics, the light is generally interacting with large surfaces, not small obstacles. But here, when the obstacle is small, the width of the when you cut your slit on a piece of mirror with a cutter, the size of the slit is less than millimeter. So it's very slow, it's very small. And you have diffraction. Okay, so in the coming slides, to explain this, what happens here, we need another model, that is the wave model. And in the coming slides, I will talk to you, I will show you how to do some very simple experiments with the ray model. But if the participants have no idea about what a wave is, you can first of all show them with water waves. What is a wave with water waves? So you can make a water container as I show here, with 4 rulers and a sheet of plastic, and then fill it with water, put it on an overhead projector, and then put droplets in droplets of water in the container, and depending on the rate of droplets, you will see this with the slow rate, and if you put more droplets per second, you will see this pattern of waves, and you can see that the water waves are spreading from the point here, the center, to the spreading from the center. This is what you get if you have 1 drop. If you put 2 drops simultaneously, this is what you can see. And this is, you see that in this path, the waves interfere, and when they is spreading from this path, they continue their way circular. They not change in the shape of it. If you don't have overhead projector, you can just take a big container of water, put it on the ground, and make the experiment. And the only difference is when you put the water container on the ground, you can't have a lot of participants around you to see it. But if you use overhead projector, you can make projection for all the classroom. So you do, depending on the situation, depending on what material you have, you can do it. Okay, now, so with the wave model, we can mainly explain the interference and the diffraction phenomena that is in module 3 in the ILOP activities. Another prediction says you have here double slits, narrow and close double slits. And the laser beam coming from laser light source has to cover both slits. And the question is to sketch what happens on the screen there. The screen has to be far from the slits. Here we say 1.5 meters, but if the slits are not very narrow, it's good if you use larger distance, that is 3 meters, 4 meters. As usual, before doing the prediction, you have to show the material. So the material is, can you see the double slits here? Dr. Yadav? This, so.
Yes, ma'am.
Okay, so you have here double slits cut on mirror. Of course, it's not easy to cut double slits on mirrors, especially if you want to put them very close together. You have to do several attempts, and you finally succeed cutting them with a simple cut. This is the covered face of the mirror, and then the laser beam, the laser light source is there. The slits are there in front of the laser beam, and the screen has to be as far as possible. To keep your laser beam, you just have to use any kind of clips. That one you use for you use for clothes. Okay. Now I want to give you 2 minutes, not 3, to remember what you know about interference and diffraction. So please, the question is to sketch what you observe on the screen. 2 minutes, please. Okay. Is you have any problem with sound or everything is okay? Hello, do you hear me? Okay, I will show you some predictions. I'm not sure whether that one is clear, but I will show you others. Okay, here in this prediction, the question asked to draw what happens on the screen, but this participant is drawing something which is happening between the slits and the screen. Okay, so we have to, when we participate, we have to listen very carefully to the question. This prediction is assuming geometrical optics. So that one is mathematics. It's not what we see on the screen. This is a participant who knows a lot about interference and diffraction mathematics. That one is close to the reality. That one also is a little bit closer to the reality. And this is a person who has certainly made the experiment before, because we have here what we call the interference fringes, but he or she, I can't remember who did this, knows something about diffraction here and interference. Because when you have, so this is, of course, after prediction, discussion, and so on, we make the experiment, and this is what you get on the screen. You see that you have fringes, bright fringes. The center is very bright, and the intensity is decreasing as you go far from the center. Thanks to this prediction, you see that the intensity at the center here is lower than here, and then lower than this, and so on. This curve is the one, if you have seen about a theory about diffraction and interference, this is what we get with single slit. So this is what we get with single slit. So with double slits, you have something that is a little bit similar to what we have with single slit, but some dark fringes in the middle because of interference of light coming from the two slits. How to understand this? You can understand this in a very simple way. Of course, I'm not saying that we can do it, study interference and diffraction without mathematics. No, but it's good to see what happens with experiment and then do mathematics without any problem. We just have to assume to do these activities. We just have to assume that a light is an electromagnetic field oscillating. Light coming from laser is a plane wave, where the electric field and electromagnetic field are perpendicular and they present maxima and minima. This is what you have to assume, and you can answer some questions about here, do light from slit 1 and slit 2 have the same wavelength as they leave the slits, if the same color, so same wavelength? Are they do have the same wavelength as the wave from slit 1, and when they reach the screen? Of course, also we can answer that they have the same wavelength when they reach the screen. Now a little more complicated the question, not very complicated. Are the waves in phase when they leave the slit 1 and slit 2? If we assume that the wave is plane, that the rays are parallel, we can answer that yes. But when they reach P, the wave coming from 1 and the wave coming from 2 are not in phase generally, because they do not undergo the same travel. I will show you why in this. So let's agree about what we call in-phase waves. What we call in-phase waves is what we have here, and the resultant at P is how to say, the intensity of wave 1 and wave 2 will be added. However, when the waves are out of phase when they reach P, when you put wave 1 plus wave 2, you will have 0. I don't know why the resultant wave doesn't appear here. Sorry, this is a problem of presentation. Here, the resultant wave at P should be another sinusoid, but with bigger amplitude, and the resultant wave here is 0. To understand better this, you can do it very easily with printing some sinusoids on transparent sheet, cut them and fix them on this piece of cartoon. This is supposed to be sorry. Okay, here, excuse me. Sorry. Okay, so here, this is supposed to be slit 1, this is supposed to be slit 2, and this is the screen. And the waves leaving slit 1 and slit 2 here are in phase. That is, we are here. You have we are in this situation. So, in the middle of your interference figure, you will have maximum here. So, because the waves will be in phase. Sorry. At another point of screen, you will also have in-phase waves that will result in bright fringe.
Yes.
Is that okay?
Yes.
Thank you. If you measure in this, sorry. Excuse me. Okay. In another situation, you will have out of phase waves. that will result in a dark fringe. So you can do this at several places on the screen, and you can understand that in the middle you will have a bright fringe. So you will have bright fringe in the middle, dark, another bright there, another dark, and another bright there, and so on. Okay, if you measure the difference way traveled by the difference between the distance traveled by the light coming from slit 1 and slit 2 when they reach the out of phase the screen, you can see that the difference is half wavelength, half lambda. But when you have bright fringe on the screen, the difference will be here equal to lambda. You can see that. Also, if you try to find the next bright fringe, you will on the screen you will see that the difference will be between the way 1, way 2 will be 2 lambda, 3 lambda, and so on. If so, this you can with this material you can fabricate several. You can duplicate it several times and give students to do the experiments by themselves. If not possible, you can do a demonstration for all the classroom. Just use this. What I'm showing here is a meter where I put colored tape, red, like here, for example, to show that the red corresponds to red light. You see on this, you can put red tape on a piece of meter and use it. This is, if you assume that this is the sinusoid I showed you before, with maximum and minimum of electric field or magnetic field, this red part is supposed to be corresponding to the positive part of the electric field. This white part is supposed to correspond to the negative part of the electric field. And the middle here is the maximum of electric field. We can also, with these models, that one or the previous one, you can see what happens if you increase the distance here between the slits. You can see or increase or decrease the distance between the slits. You can see what happens to the fringes, of course, when you increase the distance between the slits and the screen. Like here, if you put the screen here, you will see that the distance between bright fringes will increase, and so on. So here you can ask students to make prediction about what happens if you do this experiment with with slits in case A, where the slits are similar slits but very close together, and what happens when the distance between the two slits is bigger. This is the situation A, where the slits are very close, and this is the situation B, where the slits are is bigger than in A. And this is one of participants' predictions, who says that the interfringe will increase if we decrease the distance between the slits, and it will decrease. What I call interfringe is the distance center to center from two consecutive fringes, bright or dark. And this is what happens. You do the experiment after prediction. This is what you have with slits A, that is the slits which are closer, and this is what happens with slits B, which are the slits that are farther. So you can see that the fringes are bigger there than there, the size of the fringes. And if you do some measurements, knowing the wavelength and the distance between the slits, it has to be E here. Sorry, there is a mistake here. Okay, forget this. Sorry, forget this formula. Forget that one, please. It's wrong. This one, if I know lambda, the wavelength and the distance between the screen and the slits, if I measure the interfringe, the distance between the two consecutive fringes, I can calculate the distance between the slits. If you consider diffraction, you can measure also the size of the slit. What happens if I use multiple slits, if I use more than 2 slits? Here I remind you what happens with 2 slits. I have been able, after several attempts, to make 3 slits with the same width and same distance. You can see that the difference between that figure and that one is that between 2 consecutive, first of all, the bright fringes are, the size is smaller than with 2 slits. And between 2 consecutive bright fringes, you have another bright one and 2 dark fringes. If you use, you can see what happens with, you can understand why there is bright here and dark here, just using your model. Just use 3 slits or 4 slits. You will see that as you increase the number of slits, the size, I think this is with 4 or 5. I'm not the one who did this, the slits. It's very hard to do by yourself 4 slits or 5 slits. But you can buy if you have many otherwise you can understand with the model. This is what, here you have double slits, and here you have maybe 3 or 4 or 5 slits. You can see that the size, as you increase the number of slits, the bright fringes are more bright but less large. And in between 2 consecutive bright fringes, you have dark. So as you increase the number of slits, the bright fringes look more and more like spots or light spots, not like large fringes. If you use grating, this is what you will get. I mean, so what is a grating? A grating is it looks here. This is a grating. It looks like transparent media, but it has a big number of slits per millimeter. Once again, in my country, not easy to get grating, to buy gratings. You have to send money to a foreign country and wait and so on. So the best way to have your own grating is to use a CD, old generation of CD. You see, if you start cutting the CD here, the coating of the CD start removing. So you can use tape, Scotch tape, to remove the coating of the CD. So you see what happens here. Here is my CD. I have removed the coating in this place. And if I use my laser, red laser, you see that in the middle I have a very bright spot and 2 other spots in well, this is another spot, and this is first middle one, first one close to the middle one, and second spot. Please note that here I have put the screen very close to the CD, because as the slits are very close together, the diffraction will be very big. So the fringes will be very far from one another. So you have to put your screen closer to be able to see something. And if you, as you know, maybe the spot at the center is, when you are talking about grating, is called zero order. The first one on the right and the left is called first order, and the other one is second order. This is all what we can see with grating, because as I told you, the fringes are, the slits are very narrow, and so the fringes are very far from one another. You can, and last experiment with interference and diffraction, you can try to understand what happens also if we have white light coming on the slits. White light, as I don't know if you saw this in David's presentation. If you use a prism and geometrical optics, if you assume that the wavelength, I'm talking about prism now, if you assume that the wavelength depends, if you assume that the index of refraction depends on the wavelength, you can understand that the refraction will not be the same if you have different colors. This is what you see with the prism. But here also, if we use white light, and we assume that it is a lot of colors, as you saw with prism, and using our wave model with the sinusoid, you can see, if you study interference, you can see that in the middle, any color you use, blue, red, green, or whatever, you always have bright fringe. As you move from the center, you can see on this figure that the first bright fringe, blue one, occurs very closer to the center than the red one. So this will result in a spread of the white light in its different colors. In this I show only blue and red, but in between you have yellow, green, and all the other colors here. In this sinusoid model, I used blue wavelength, almost half of the red wavelength. This is a prediction of one of the participants who knows visibly what happens with when you use grating. This prediction says exactly what I was telling you with the sinusoid, that in the middle you have superposition of all colors that results in white light, and on the right and on the left you have a rainbow with all the rainbow colors. He is a very good student here because he knows that before blue we have violet. Our human eye is sensitive to violet also. So when you use grating and white light, you will have bright fringe in the middle and two rainbows on the right side and left side. You can explain what happens with white light once again using your this tool. I don't know how to call it, ribbons or something like this. You can do demonstration for all the classroom as we are doing here, and just make sure that when you use grating and your light source, you have, if you want to see what happens, if you want to see what we call dispersion of the white light, now it's a dispersion with grating, not with prism. You have first to put a slit on your torch. Otherwise, you will not be able to see the dispersion of the light. And you see, I am using here grating coming from a CD. Of course, in a good grating, the slits are parallel, but if you use a CD, the slits are a little bit curved, but you can see on this slide that the result is not. If you want to have to see better dispersion with grating, you can do this with a spectroscope. I love this spectroscope so much because it's very funny. You can do many things about your spectroscope. How can we construct your own spectroscope? Very easily. You just need a tube that will be your dark chamber. This dark chamber, you have to close it from both sides by one slit on one side. On the other side, you will make a window. You will fix a grating, a piece of grating coming off from a CD. You can see here, I have fixed the piece of grating coming from the CD on the window, and then put it on the other side of the spectroscope. Please, when you fix the grating, make sure that the slits of the grating are parallel to the slit you put on the other side. Generally, when we do our active learning workshops, we ask participants to construct their own spectroscope. We ask them to bring tubes like this, like you see on this. Okay, here you see participants. Here are participants from Pune, India, and here are participants from, I think, Cameroon, Africa. It's a lot of fun when we fabricate the material, when we do active activities, fabricating the material. It's really always a lot of fun. And then how to use your spectroscope, you just put your eye on the window, not on the slit. Put your eye on the window, and so that the light will enter the spectroscope by the slit, go to your eye, and you have to pay attention to what you will see inside the dark chamber. What you will see exactly is this. Depending on the light source, if it is sunlight or if it is discharge lamp or 3 colors LED. Here you have a spectrum you get from 3 colors LED. I think here is discharge light source. You can see spectroscopic lines of the gas inside the very bright lines. You see here green, blue, violet, and the green, very bright lines, characteristic of the gas inside your light source. This has something to do with quantum mechanics, and it's very nice to see this. This spectrum comes from sun, I think, and it's a continuous spectrum. Okay, so this spectroscope is a lot of fun when we use this spectroscope. Now, very quickly, I will show you some other experiments on atmospheric optics. The first, of course, on this slide, you can see that atmospheric optics atmospheric phenomena having something to do with optics are various. You can see on this slide, the difference between the phenomena depends on the phenomenon, what happens to the light, if it is scattering, refraction, diffraction, or interaction with the electric magnetic field, and it depends on what is in the air. If you have aerosols, if you have water, if you have ice, if you have ionized air, depends on the atmosphere. You know that in the atmosphere you have many layers, and each layer is characterized by particular conditions. Okay, I think you saw I will focus on two particular phenomena, that is scattering of light in the atmosphere, and what else? You cannot see here and polarization of the light, of the scattered light. The most common phenomena, atmospheric phenomena, I think, is rainbow, and you can explain easily rainbow using geometrical optics, as I think David showed you in the first conference, using Snell laws and index of refraction of transparent media. Before talking to you about what happens in atmosphere, I just want to remind you something about multiple reflections. By doing this experiment. In this experiment, I take I have a cup containing water with soap, and I use a straw to make bubbles. You make bubbles with in the straw, and then you shine the bubbles. If you see here, the bubbles are transparent. If you shine the bubbles with laser, here I am using green laser. Generally, if no bubbles, the light from the laser will go straight, as I told you before. When the laser beam comes on the bubbles, you can see that all the bubbles become green. Why this happens? This happens because multiple reflections on the bubbles. If you turn the light off, you can see that the bubbles look, you cannot see the bubbles anymore. You see only something green. Why I am showing you this multiple reflection? Because this helps you to understand what we call, because here I am using, in this experiment, what happens is interaction of light with bubbles, which have interaction with the bubbles are some kind of droplets of water with a relatively big diameter comparatively to the wavelength of the light. But if I use, instead of bubbles in the water, if I use milk, fat milk molecules, the diameter of the fat molecules are very small comparatively to bubbles. So in the picture here, I have two cups filled with water with very few, 2 or 3 droplets of ink. Here I have cups of water with few droplets of milk. Now, the change from here to here is that one of the cups is shined by white light from the bottom, the other one without light. This one is not shined, and here I put white light. What you see is not big change in the color of the water plus ink in that case. And in that case, there is a big change. You see that the water with milk here become very bright. So what happens here is that with ink, the light is absorbed by ink. But in that case, the light is coming from the bottom. I don't know if you see the blue light torch in the bottom. Can you see it? You have blue light.
Yes.
Yeah, and the light is going from the bottom to the top of the glass, and you see the glass becomes bright because the way of light is changing from going from bottom to top to your eyes. That is, we call, it's kind of multiple reflection, but when the multiple reflection is done by very small particles, we talk about scattering. In the coming slide, can see that I use filters, blue, green, and red, to see what happens to the torches here are on. 3 of them are on, and in the glasses I have water plus milk. You can see that if I use all, of course, if you use white light, it's all the rainbow colors, but I use, here I'm using only 3 colors. You can see that all the colors are scattered. Blue, green, and red are scattered. The question is, are they scattered in the same way? In this picture, I am using aquarium containing water with milk once again, and I am shining the container with 3 LEDs, red, green, and blue. Unfortunately, the picture is not as clear as what I did with the experiment. You can see that the blue is more scattered than the red. You can see, if you go in this side, you can see that the red is, since the red is less scattered, it's able to undergo a longer distance in the liquid than blue, in the water plus ink liquid. You can see this in another way. In this diagram, I have here my container with water and milk. The incident light is coming from there. If I look to the top of my container, I am going to see the scattered light. If I look to this part of the container, it's once again what I will call scattered light. If I look from this side of the container, I am looking the transmitted light. And what I am going to see is that, as I show you here, the picture from the top, taken from the top of the. So as I told you before, the blue is much scattered than the red. And if I look to the transmitted light here, this is what I am going to see. Not very clear once again, but you can see that you have more red here than blue. And you can understand what happens, why by comparison, why the sky is blue and why the sky is blue at midday, for example, you can understand the red sunset. What happens when you see the sky at midday? You don't look in the direction of the sun, but if you see in other direction, the sky is blue because you see the scattered light. However, in the afternoon, when you look at the sunset, you are looking in the direction of the sun, so you are looking to the transmitted light in the atmosphere. And at the sunset, the light is traveling a very long way on the atmosphere before reaching your eyes. So you can understand like this blue sky and red sunset. Last demonstration is about polarization by scattering. If I have the container here with water, and I have unpolarized incident light. The question is, what about the scattered light and the transmitted light? You can make of course, if you can make prediction, but I will show you the experiment that here is the container containing water with milk. This is my white light source, and here I put on this side of the container, I put two polarizers, one with transmission axis vertical, and the other one here with horizontal transmission axis. You can see in this dark part where I have superposition of the polarizers that the axis of the polarizers are perpendicular, that one and that one. So the conclusion here is that the scattered light is partially polarized. Okay, since you have this one darker than here, so how is it polarized? It is polarized vertically. If you see from the top part of the water container, you will also have polarized light because it's scattered light, same thing from here or from here. However, if you see the transmitted light, I didn't put pictures about transmitted light, you have no polarization. So if we summarize here that the scattered light is polarized vertically here and horizontally, if you see from the top, and the transmitted is not polarized. This container with water with milk is supposed to simulate the atmosphere. So the question is now, if you are there and you are sun rays coming from there, if I ask you a question, in which direction, A, B, or C, you will see the sky significantly polarized. I will give you just 1 minute to think about this question. This is my students having pieces of polarizers that they use to analyze the polarization of the sunlight. You see, if you see the shadows of the students, you can understand that the sun rays are coming in this direction, from this direction, and they are looking to the scattered light. They don't have to look in this direction, the sun direction, but they have to look in the other direction. And you can see this girl is looking something that looks like direction B in the diagram. That one is looking something like A, and this one something like C. This one is wrong. He's looking to the sun. He will have his eyes tricky. And if I come back to this experiment, the previous one, you can see that the polarization occurs when I am observing the rays perpendicularly to the incident light. So if the incident light is here, the perpendicular direction is something like this girl is doing, and she is able to see some polarization. If you want to do the experiment, please make sure that no clouds, no pollution in the sky, otherwise you will not be able to see the polarization. So no humidity, no clouds, no pollution, and then you will see the polarization of the sky. Here are our colleagues from Pune also taking the polarization of the sky. Okay, of course, we can do a lot of experiments, very simple and very interesting experiments to understand optics concepts and laws, but I showed you very few from what you can find in the UNESCO active learning activities, just to show you that you can do a lot of experiments without buying very expensive material, and you can get very interesting results. As now I am going to move to module, the two last modules, just to show you very quickly what we can do with all the activities you do in the 4 first modules. I'm going to show you what I did with secondary school students. 4 of them, they are there. The youngest one on this picture are secondary school students. The other persons are teachers and me in the middle. The experiment we did is about how is about sound and how to take sound from one place to another to communicate, how to communicate with sound. Okay, so the students did all the project. I'm going to go very quickly just to show you that they did some bibliography about how do people started communicating from in some during the time. So this is a way with tam tam, pom pom pom, with smoke, with the telegraph, with the string phone, with phone, and nowadays with the modern ways of communication. So the students were able to understand what is sound, that is a propagation of mechanic perturbation in the air. They were able to construct what a toy we used to construct when we were young children. I don't know if nowadays the children use this toy, but with my sons I did it. String phone, you can use very simple system with a string, 2 caps, and just it. I mean, you fix the string in the bottom of the caps, and you have to keep the string straight, and you are able to communicate with another person. Just make sure that the string is straight and it doesn't touch anything, chair, door, or something. Okay, then they made bibliography about how telegraph works, and we tried first to make a simple LED optical telegraph with a very simple circuit. The first one I showed you with a light source, which will be what we call a transmitter, a receiver, very simple also with a photoresistor, battery, and beeper. So if when the photoresistor will receive light, the photoresistor will allow the currency going inside the circuit, and the beeper will beep, 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 beep. If no light, no beep, of course. I show here the parts, very, very cheap, very simple. Once again, the most expensive part is the battery in this simple telegraph. Here you have pictures of students making the circuits. You see, they are using the parts with a piece of hard paper, carton. They can fix the parts on the piece of carton, and they also can make some soldering here. Believe me, I learned a lot when doing those activities. I never did soldering before. I did soldering while working with the students. It was really very interesting and very nice. So here is our emitter with the LED, and here is the receiver with the photoresistor here and the beeper. And with the interrupter here, when the interrupter is on, light, the LED is on, emits light, and the beeper will beep, 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 and then if you stop the light, you stop, the beep stop, and then this is a kind of telegraph, because depending on the frequency of on, off, beep, 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 the beeper will, you can send signals with the beeper. Okay, of course, you can, while doing the experiment, you can see, since the LED is a diverging light source, if you move the receiver a little bit far from the emitter, the transmitter, you will lose signal. I mean, no more beeps. So the best way is to do what? If you increase the distance, is to use optical fiber. And on this picture, you see the beep, the LED, the emitter is there, the receiver is there with the photoresistor going to in this direction, and the light is undergoing the optical fiber, and it works. Very simple, but it works. Now, for modern optical voice communication systems, the students could easily understand that you just have to take sound coming from computer or from phone or radio as electric signal. Okay, with the emitter, you can print the sound signal on a light wave, so you get a modulated signal, and then you send the light signal will be modulated by the sound. You send the modulated sound to the receiver, and then you will get with the photoresistor, then you will get the electric signal with the same characteristics than the original sound. Then use a microphone to remit the original signal. So here is the figure of the emitter, the receiver with the audio signal. The modulation happens here, the LED with the modulated light signal, the receiver, and the microphone to reproduce the audio original signal. The students did a lot of circuits. They did the circuits on as as you see here on electronic special tools, and they were able, here we have signal coming from a computer, or as I told you, phone, and it works very, very, very well. They also understand how to emit multiple signals by using, instead of one color LED, they used 3-color LED. You see here how they understand how a 3-color LED works with 3 interrupters, and they understood. And then they put the 3-color LED in a circuit more complicated than the first one, because in this circuit you can use the 3 channels. Each channel will be used for one sound 1, sound 2, side 3. Here are the audio connection coming from computer. And okay, so it's same slide I showed you before. And then after making several tests, they have fixed this multiplexing circuit. Here are the 3 supports for the audio signal, signal 1, signal 2, signal 3, and this is the 3-color LED. I show you here many kinds of circuits. I had really very nice students, secondary school students. They did a very good job. All those circuits were done by secondary school students. And then here, when you send the signals on this 3-color LED, as I told you before, all of them are diverging. So to separate the 3 signals, you just need to use grating. Okay, the grating will separate the 3 colors. Remember that each color corresponds to a sound signal, and if you put your photoresistor receiver here, you will get the signal corresponding to the blue color. If you put here, you will get the signal corresponding to the green color, and here you will get the signal corresponding to the red color. Of course, when you need to use optical fiber between emitter and receiver, and nowadays you can send a lot of big of information, not only 3 on optical fiber. Here are my secondary school students enjoying really their activities. In conclusion, I hope that I could convince you that this innovative active learning approach are very attractive and very well adapted to teaching physics in our developing country. As I told you, the students are not there in the classroom listening to the professor, but they are engaged in the learning process. These are not only hands-on activities, but they are also hands-on, minds-on activities and learning. Because why I am saying this? Because I don't know how are done practical activities in your universities, but generally students do not, when they do practical activities, they only try to get the result, to get points, not to understand the physics phenomenon. The material is simple, inexpensive, easily constructed, or if you buy some like battery or other electronic parts, not really expensive. Of course, you need volunteering, availability, and generosity if you do active learning. Believe me, you have to give a lot of time to make the material, to conduct the activities in the classroom, but it is a lot of fun if you love physics. It's okay, I think. Okay, very quickly, I will tell you about how did I came to active learning. On 2006, I attended the first ALOP workshop in Tunisia, and I loved active learning. So in this picture, I am there as a participant in active learning. Sorry?
No, madam, please continue, ma'am.
I'm almost done. I will just 2 or 3 slides. So after this 2006 workshop, we made a small team with our colleagues. You see some of them here, and we duplicated all the ALOP lab experiments we did. We translated the manual from English to French in collaboration with the Moroccan team, because in Morocco the second language is also. And then this is the manual, the French manual, translated manual from. In 2007, I was invited by the original ALOP team to. Sorry? Sorry?
Somebody has accidentally.
Okay. Okay, so 2007, it was my first experience as a facilitator, not as participant. It was really wonderful. I did part of not a whole module, but part of one module, and it was a wonderful experience. And since that time, I became part of the international ALOP team. Let me tell you that when we do such kind of active learning workshops, we take the material, as I told you before, with us, and we let the material, if I go to secondary school or to some place in Tunisia or not in Tunisia, in Africa or whatever, in Pune, or we let kits of material to the two groups of participants in case they want to use or duplicate or something like this. This is the picture of my kitchen this morning. I was taking some pictures about scattering with milk. It's always like this. When you do active learning, you are doing experiment anywhere you can do experiment. And also, if you understand properly what happens in module 4 about atmospheric optics, believe me, you never look. You look to the atmosphere, to what is surrounding you in another way, not a different way before attending the workshop. Special thanks to the original, to the creators of ALOP team for the creators of ALOP workshop for inviting me to be part of the team. As I told you, it was a lot of very interesting for me, for my students, and for my teaching in general. Once again, many thanks for inviting me to be part of your workshop. And if you have some questions, I will be happy to answer.
Thank you very much, ma'am.
Thank you.
Dear participants, the session is now open for discussion. If you have any questions, you can raise your hand and unmute yourself and ask the question.
No questions?
We'll see if there are any questions.
On these pictures, my hair is colored. Now I decided to no coloration.
Yes.
So this is the original.
Yes.
Okay, maybe everything was clear. No questions.
Yes, yes. Yes, ma'am. Everything you have covered, right from basic things to applied things in a nice manner. And everything it was through experiment and active learning.
Yeah.
That's why it was very easy to understand the things. The prediction sheets you used, that also helped a lot.
Yeah.
Thank you
Please,
very much.
please note that I gave you the link to download the manual. If you
Yes,
want to, if the participants, I mean, want to fabricate material, if you need any help, please give my email address. I will be happy to help.
Yes, ma'am.
Okay.
Yes,
because
yes,
this
sure.
is all the material. Sorry.
Yes, I will provide your email ID.
Okay.
Yes.
No question.
No questions. So I request my departmental colleague, Professor Maruti Kumar, to propose a vote of thanks.
Thank you very much. Thank you to everyone there. Bye.
Yes.
Thank you very much.
Yeah, 1 minute, ma'am.
Thank you, sir.
1 minute. 1 minute. Yes. Kumar, sir, please.
Thank you, sir. It is a great privilege to propose a vote of thanks on the occasion of the Faculty Development Program. On behalf of my college and the Department of Physics, Electronics and the Photonics, I am very hearty gratitude to eminent and the enthusiastic resource person, Professor Suhaila Lahmar from Tunisia, who has shared very fruitful thoughts on active learning in developing countries, some examples in the teaching optics. Ma'am, I think a good teacher can inspire hope, ignite the imaginations, and instill a love of learning. Teaching is a very noble profession that shapes the character, caliber, and the future of an individual. Ma'am, at this age, also you are teaching means you are inspiring us, encouraging us with a lot of energy to do great work. You have given the thoughts on the active way of the teaching, problems in developing countries in active learning, and how to solve those problems with a simple equipments. Ma'am, you have given the way build up of the simple module to understand the physics in very easy way. Definitely, ma'am, that will help us. Thank you, ma'am, for such a fruitful session.
Thank
I
you.
extremely thanks to our principal, Honorable Dr. Mahadev Gawani sir, for supporting us to organizing such beautiful event. I extremely thanks to Honorable Dr. Abhijit Yadav, young scientist, head of the department, Physics, Electronics and the Photonics, and the coordinator of this FDP, for inviting us such an enthusiastic resource person. I also want to thanks to the heads of various departments, faculty members, research scholars, and the students for attending and the kind cooperation in making this session as a successful. Finally, I would like to thank my colleagues and whole organizing team. So finally, thank you all for your kind attention. Thank you, ma'am. Thank you once again.
Thank you, dear colleague. Thank you so much. Thank you, all the participants. Thanks, the organizers. And ciao.
Thank you, ma'am. Thank you very much.
Bye. Thank you very much.
Thank you very much.